A camera the size of a small car just took a picture of the universe, and inside that single exposure, scientists found 11,000 objects that no human being had ever seen before. Not in a decade, not in a lifetime of searching. In a matter of weeks, somewhere in the mountains of Chile, a machine built to watch the sky move in real. Time had just quietly rewritten the known inventory of our own solar system, and it was only just getting started. This is the story of the Vera C. Rubin Observatory. And before you decide, you already know what it found, you should know this. The headlines, calling it the machine that changed everything we know about the universe, are getting ahead of the truth. What Rubin has actually done is stranger, slower, and in some ways more thrilling than any single discovery could ever be. It has not rewritten physics. Not yet. What it has done is switch on the most powerful eye humanity has ever pointed at the sky. And in its very first weeks of blinking open, it has already shown us that the universe we thought we understood is far busier, far stranger, and far less finished than we believed. To understand why this moment matters, you have to go back nearly 50 years to a woman named Vera Rubin, standing in a dim observatory dome, staring at strips of photographic film that did not make sense. Rubin was studying the Andromeda Galaxy, our closest large galactic neighbor, and she was measuring something simple: how fast the stars at the outer edges of the galaxy were moving compared to the stars near the center. By every law of physics known at the time, stars far from a galaxy's core should orbit more slowly, the same way Pluto crawls around the sun while Mercury races. But that is not what Rubin saw. The stars at the edge of Andromeda were moving just as fast as the stars near its heart, as if some invisible hand were gripping the entire galaxy and forcing it to spin together as one rigid disk. Rubin and her collaborator Kent Ford checked the data again and again. Today we call it dark matter, and it is believed to make up roughly 85% of all the mass in the universe. Rubin spent the rest of her career chasing its shadow, and she died in 2016 having proven that it existed without ever seeing it directly. No telescope, no camera, no experiment on Earth has ever captured dark matter itself. We only know it is there because of what it does to everything around it. Now, a decade after her death, an observatory bearing her name sits atop Cerro Pachon, an 8,800-foot mountain in the Chilean Andes, built specifically to finish the hunt she started, and it is not a modest instrument. At its heart is the largest digital camera ever constructed for astronomy, a machine roughly the size of a small car, weighing over 3 tons, capable of capturing images at 30-200 megapixels. To put that number in perspective, if you tried to display a single one of its photographs at full resolution, you would need 400 ultra-high-definition television screens standing side by side just to view it in full. Each exposure the camera takes covers a patch of sky 45 times larger than the full moon, and it can do this again and again, all night, every clear night, for 10 straight years. This is not a telescope built to stare at one object for hours the way older instruments do. It is built to scan the entire visible southern sky over and over, capturing every star, every galaxy, every flickering light source it can find, and then compare each new image against the last, hunting for anything that has changed. A new light that wasn't there yesterday, a star that has dimmed, a speck of rock that has moved half a degree since the last exposure. Astronomers have a name for this approach. They call it the legacy survey of space and time, and the ambition behind it borders on reckless. Over the coming decade, Rubin is expected to generate roughly 20 billion images of around 40 billion astronomical objects, more raw data in a single year than every other optical telescope on Earth has produced combined across the entire history of astronomy. The survey formally began in the summer of 2026, after years of delays, testing, and what the observatory's own leadership called a careful process of technical validation, because when you are about to generate more data than has ever existed in the field, you do not get a second chance to get the calibration wrong. And almost immediately, before the 10-year clock had even properly started ticking, the early test images began revealing things that stopped scientists in their tracks. During what were meant to be routine system optimization runs, imaging meant only to check that the cameras, the mirrors, and the software were working correctly. Rubin detected more than 11,000 previously unknown asteroids. 33 of them were near-Earth objects, the class of asteroid that orbits close enough to our planet to matter for planetary defense. 380 were trans. Neptunian objects, distant icy bodies orbiting out past Neptune in the frozen dark at the edge of the solar system, a region so poorly mapped that every new object found there reshapes our understanding of how the outer solar system formed. And this was not the observatory working at full capacity. This was Rubin essentially clearing its throat. Think about what that means. Every asteroid survey that came before this one, every observatory, every dedicated planetary defense program built over the last several decades has cataloged roughly 1.5 million asteroids across the entire history of organized astronomy. Rubin found 11,000 new ones in about a month and a half, while it was still being calibrated. Scientists working with the observatory have projected that once the full 10-year survey is underway, Rubin alone could discover millions of new solar system objects, essentially doubling or tripling the known population of asteroids, comets, and distant icy worlds, in a fraction of the time it took humanity to find the first batch. This is not a small technical footnote. This is the difference between mapping a coastline with a rowboat and mapping it with a satellite. For the first time, our species is close to having something resembling a complete inventory of the objects sharing our solar system, including, crucially, the ones that could someday be on a collision course with Earth. But asteroids are only the beginning of what Rubin was built for, and honestly, they are almost a side effect. The real target, the reason the observatory carries Vera Rubin's name at all, is dark matter, and its equally mysterious cousin, dark energy. If dark matter is the invisible glue holding galaxies together against forces that should tear them apart, dark energy is the opposite kind of mystery entirely. It is the name scientists have given to whatever is causing the expansion of the universe to accelerate. Not just expand, the way it has been doing since the Big Bang, but speed up, as if some force is actively pushing every galaxy away from every other galaxy faster and faster with each passing year. Together, dark matter and dark energy are believed to make up around 95% of everything that exists, which means the stars, the planets, the galaxies, every human being who has ever lived, every atom we can see, touch, or measure directly accounts for less than 5% of the universe. We are, quite literally, living inside a universe we can barely perceive, surrounded on all sides by something we cannot see, cannot touch, and until recently could barely even prove was there. This is where Rubin's design becomes almost poetic. By photographing the same patches of sky over and over for a decade, the observatory is not just looking for things that move, like asteroids. It is looking for things that bend. Massive concentrations of dark matter warp the fabric of space itself, and that warping subtly distorts the light from galaxies behind them, an effect called gravitational lensing. It is an incredibly faint signal, invisible in any single image, but by stacking tens of thousands of exposures of the same region of sky, and measuring how the shapes of distant galaxies are stretched and smeared with almost impossible precision, astronomers can begin to map where dark matter is hiding, indirectly through its gravitational fingerprints across billions of light years of cosmic real estate. At the same time, Rubin is hunting for something called stellar streams, thin, glittering rivers of stars that were once part of smaller galaxies or star clusters, torn apart and stretched into long trails as they were slowly consumed by the gravity of the Milky Way. These stellar streams act almost like scars, recording the history of violent gravitational encounters, and scientists believe that studying exactly how they are twisted and disrupted can reveal the distribution of dark matter within our own galaxy, essentially letting us reconstruct an invisible skeleton by watching how it has bruised the visible universe around it. And then there's the deep field. In early August of 2026, astronomers released one of the most staggering single images to come out of the observatory so far. A deep exposure of a patch of sky known as the Cosmos field, a small region that has become one of the most intensively studied targets in modern astronomy. The same patch of sky has already been photographed by the Hubble Space Telescope, by the James Webb Space Telescope, by the Chandra X-ray Observatory, and by the Spitzer Space Telescope. Each of those instruments captured a different slice of the story. X-rays revealing violent black holes, infrared light revealing the faint glow of the earliest galaxies, visible light revealing structure and color. What Rubin added was depth and breadth on a scale none of those missions could match on their own. An exceptionally deep, wide view of the same crowded slice of sky, allowing scientists to layer Rubin's data directly on top of everything, gathered by humanity's other great eyes in space and on the ground. It is less like a single new discovery and more like finally getting the missing puzzle piece that lets an entire picture snap into focus. When the second phase of that early data release rolls out later in 2026, it will include something even more valuable to scientists hunting for cosmic change. Difference images, frames that isolate only what has changed between one exposure and the next, stripping away everything static and leaving behind just the flickers, the flares, the sudden brightenings and dimmings that mark the universe in motion. This is the feature that makes Rubin genuinely unlike anything that came before it, and it is the one that keeps astronomers awake at night in the best possible way. Because the observatory does not just take pictures, it watches. Every single night that the skies over Cerro Pachon are clear, Rubin captures roughly 1,000 images, and its software compares each new frame against a master template built from previous observations, hunting automatically for anything that has changed. When it finds something, a star that has suddenly exploded, a black hole that has abruptly begun feeding on nearby gas, an object that has moved against the background stars, it does not wait for a human being to notice. Within seconds, it fires off an automated alert to astronomers and telescopes around the entire planet, essentially shouting into a global network, "Something just happened here. Come look immediately." In its very first weeks of alert operations, before the full 10-year survey had even formally begun, Rubin was already detecting supernovae, the explosive deaths of massive stars, along with variable stars that pulse and dim on predictable rhythms, and active galactic nuclei, the blazing cores of galaxies, where supermassive black holes are actively devouring matter and radiating enormous amounts of energy in the process. Scientists working with the observatory have described the system in almost cinematic terms, calling it the beginning of the greatest cosmic movie ever made, a real-time decade. Long time lapse of an entire hemisphere of sky in which nothing that flares, explodes, or moves will go unnoticed for long. This capability connects to something even stranger sitting at the frontier of physics, multi-messenger astronomy. For most of human history, everything we have ever learned about the universe came through a single channel, light. Visible light, then radio waves, then X-rays and infrared and gamma rays, but always light, always photons traveling to us across unimaginable distances. In the last decade, that has started to change. We can now detect gravitational waves, ripples in the fabric of space-time itself caused by cataclysmic events like colliding black holes or colliding neutron stars, first directly observed in 2015 in a discovery that reshaped modern astrophysics. We can detect neutrinos, ghostly subatomic particles that pass through entire planets as if they were not even there, occasionally originating from the most violent events in the cosmos. The problem has always been connecting these different signals to an actual visible source. A gravitational wave detector might sense a ripple from two neutron stars colliding somewhere in the sky, but it cannot tell you precisely where to point a camera, only a rough, enormous patch of sky that could contain thousands of galaxies. This is exactly the kind of problem Rubin was built to solve. Because it is constantly rescanning the entire visible sky and instantly flagging anything new, when a gravitational wave detector or a neutrino observatory sends out an alert about a violent cosmic event, Rubin's archives and ongoing observations can be searched almost immediately for a matching flash of light in that same patch of sky, potentially catching the visible afterglow of an event that was, until that moment, only a ripple in space-time and a burst of ghost particles. For the first time, astronomers have a realistic shot at watching the same cosmic catastrophe with multiple, completely different senses at once, light, gravity, and matter, stitched together into a single, richer story. It is worth pausing here to be honest about what Rubin has and has not done, because separating verified science from speculation is the only way any of this actually means something. Rubin has not discovered dark matter directly. No instrument on Earth has. What it has done is begin assembling the largest, deepest, most precise dataset ever built for hunting. Dark matter's gravitational fingerprints, and it will take years of continued observation, data processing, and careful analysis before any definitive new claims about the nature of dark matter or dark energy can be responsibly made. Rubin has not found an alien signal, has not detected a rogue planet threatening Earth, and has not overturned the standard model of cosmology in a single press release, despite what some headlines might imply. What it has done, in just its first weeks and months of operation, is discover more new asteroids than most dedicated survey programs find in years, capture one of the deepest and widest single views ever taken of a patch of extragalactic sky, begin generating real-time alerts for stellar explosions and flaring black holes on a scale no observatory has attempted before, and lay the technical foundation for what many astronomers genuinely believe could become the most scientifically productive single instrument in the history of the field. The revolution Rubin represents is not a single lightning bolt of revelation. It is closer to a dam breaking, a slow, relentless, accelerating flood of data that will, over the coming decade, very likely rewrite entire textbooks, not because of one headline discovery, but because of the sheer, staggering accumulation of everything it sees. And there is something almost unbearably human buried inside all of this. Vera Rubin herself spent her entire career being told, in various quiet and not so quiet ways, that a woman studying the outer edges of galaxies was pursuing a peripheral, unglamorous corner of astronomy. She was denied access to observatories that did not permit women on site. She competed for scarce telescope time against colleagues who had far easier access to the world's best instruments. And she kept measuring rotation curves anyway, kept staring at data that did not make sense, kept refusing to explain it away, until the anomaly became undeniable and reshaped the field around her. She never won the discovery she was chasing in the way she might have hoped. She proved dark matter's gravitational influence beyond serious doubt. Attempting to finish the question she spent her life asking, There is something quietly devastating and quietly beautiful about that. The woman who could never see dark matter built, in a sense, the machine that might finally reveal it, 60 years after she first proved it was hiding in plain sight. Because, make no mistake, what Rubin is chasing over the next 10 years is nothing less than a more complete picture of what the universe is actually made of and how it will end. Every model of the universe's ultimate fate depends on understanding dark energy, that mysterious force accelerating cosmic expansion. If dark energy remains constant, the universe will keep expanding forever, galaxies drifting apart until the night sky of the distant future contains almost nothing visible at all, a slow, cold, silent fade into darkness. If dark energy is changing, growing stronger over time, some models predict a scenario physicists actually call the Big Rip, in which the expansion eventually becomes so violent that it tears apart galaxies, then stars, then planets, then atoms themselves, ripping the entire fabric of reality apart at the seams. We do not currently know which future we are heading toward. The honest, current answer is that we do not have enough data yet to say for certain, and that is precisely the gap Rubin was built to close by measuring the distances and movements of an almost incomprehensible number of